just to make sure, for those of you who may have not been here last time, keep us all on the same page in terms of class expectations. Next thing you have to do is a formative assessment. So this is not available yet. I will put it up after class because I wanted to see how far we get and therefore what I can ask you. This is the one that, even though it's called a quiz in Icon because they didn't have a formative assessment link that I could click instead, it's not graded. I check to see that you did it and I give you your points. The idea is that it provides us with some way of doing structured review. Homework 2 is almost done. I just need to double check it and make sure that everything is correct, and I will send you an email once that is posted as well as the quiz. Homework 2 is due the following week. This is going to be over the same types of models in example 3, so we'll make sure that we finish that today and review that so that you're feeling good about that. It will include lots of questions that you can't use Excel for. So if you've been fighting learning SAS or Stata, now is the time to bite the bullet and join the club. All right, so I was debating where I wanted to start today because I want to do some review and I want to make sure we cover all of this stuff. So how about we start with this handout just to make sure that you understand the pieces that you will use to complete your next homework. So this is example 3. We've been in this for a couple classes now. So one thing I am going to change on your homework is that I'm giving each of you an Excel file rather than a CSV file because there were so many issues with CSV and I don't know why. So it will be a different extension. When you run your proc import, it will say XLS and then this will say XLS as well. I will give you starter code as usual so that you can hopefully get it running. But I would also, when you're planning on working on your homework, bring your homework 1 syntax with you because then you have a record of how you were able to successfully get your data in, and then hopefully it should just be a question of changing the name of the file to be homework 2 instead of homework 1. Okay. In homework 2, you may have to make one new variable, but it won't be one of these things. You won't have to do any z-scoring. You will need to run means. So,
we will?
Yes.
Okay. Are we in that 4? Example 4?
This is 3. We're still in 3. We're going to start 4 today or next time, depending on time permitting. So I'm not asking you to ask the Google for anything. Everything that I'm going to ask of you is in here. You just have to find it and figure out what to change. So for instance, in this proc, to be able to run means, what the things that you'll need to change, data set name, right? Because this data set is specific to this example. So yours will be called homework 2 or whatever you've called it. Likewise, var here, what does this var mean? Variable. It does not mean variance, even though they're both abbreviated the same way. These variables are names that are specific to this data file, so this will need to be changed to be the variables that you are going to examine means for. One thing that was confusing, if you add additional things here, so what comes out of proc means if you do nothing else are these 5 columns: sample size, mean, standard deviation, minimum, and maximum. Last time in your homework, I also asked for variance. And so if you were to ask for variance by adding the word var here, that's all that would come out. So you have 2 options. You can either make 2 copies of this, right? The first would give you these 5 columns. The second would give you 1 column with variance. Or you can do it one time and write out the names of each of these along with variance. Then you get everything in one shot. If you haven't started doing so, rather than changing this each time to be a different question, keep a record of what you've done. That way you have every single answer to every single question in sequence. Reproducibility, we call that, right? It's important, not just for science, but for your own sanity when you come back to things. You'll note that I have comments in here. Get in the habit of making your own comments, not just what you're doing, but why. So if you want to remind yourself that this var means variable, you can make a comment as to that. Anything that starts with an asterisk is a note to yourself called a comment that the program will then ignore. I won't need you to make any pictures, but this is how we would do that. You'll see more of these today. Proc univariate, excuse me, gives you all kinds of additional descriptive statistics such as median, mode, quantiles, percentiles, and that kind of thing. Let's see, this is the Stata version. So those of you who are going to have to pledge allegiance to Stata at some point in your life, I think, Terry, you're in that group. And the other people who are not here at the moment, are you in that group? Jeff? Still Jeff? Still Jeff today? Just checking. I want to make sure we didn't miss anything. So it would be good if you could, if you have the time to try and do your homework either in Stata to begin with or to replicate it if you do it in SAS first. That way you have a record in Stata for your own self that you can refer back to when you need to use it in the future. For those of you who have the time, learning 2 programs instead of 1 is 2 lines on your Vita instead of 1. So that's always a good thing. Proc T-Test. This is an example of how you would test a sample mean against a population mean. You're going to have to do that. So HO in this case, that's your hypothesized population mean is the null hypothesis. That's your reference point you're testing against. Do you remember what 2 sides means?
Two-tailed.
Yep, and what does 2-tailed mean? Yep, this. Yeah, your distribution, and that you care about whether it's too big or too little. Both are valid things to be extreme. Yes. In my world, everything is going to be 2-tailed. I will never ask you to do 1-tailed because I kind of think it's bullshit. But that's a whole separate philosophical conversation. Alpha, what's that?
That's aberrant.
Aberrant or abhorrent. That was the other one. I kept wanting to stick an H in aberrant. It's the area that you're considering to be extreme. So if I have an alpha of 0.05, that means that only less than 5% of the time is where I'm saying something is extreme enough to be noteworthy, to say it's not likely to be 0, to say it's significant. Yeah.
I have a quick clarifying. So the 0.05 for the alpha, is that split?
Yes.
So it's in each, okay.
Yeah, it's 2.5 on each side.
Okay, so it's not per side.
Right.
Gotcha.
If per side, if it's 5 per side, that would be an alpha of 0.1. And so that's the difference, is where you're going to load your 5.
Mm-hmm.
So if you did a 1-tailed test, the critical region is closer to the middle because all 0.5 is out here, and then the other side you're just pretending doesn't matter. And so you're stacking the deck in one direction. Yes, good question. And let's see, I'm not making you do anything for variances, so that's not relevant. So hopefully most of this is fairly straightforward to read. What's the difference between standard deviation and standard error? Feel free to read from the screen.
Sample versus population.
Keep talking.
The standard error is like all the samples in the population.
Standard error is how far off the sample mean is from the population mean on average. Standard deviation is how far off one case is from the sample mean on average. So standard error refers to the 12 packs. Standard deviation refers to the cans. That's my metaphor for populations.
Can you repeat that one more time?
Yeah. So we talked in class about the idea of testing a Mountain Dew can against the target of 12 ounces. So if I have a sample mean, say, of 13 ounces, hooray, I got extra caffeine today. Standard deviation is how far off on average each can in the 12-pack is from the mean. Standard error is how far off each 12-pack mean is from the 12 that it's supposed to be. The 12-pack meaning sample, can meaning respondent. Okay. So the logic then in forming a confidence interval, this gives you the expected range of variability around the mean as dictated by that standard error. It's roughly 2 standard errors around the sample mean. So if the population mean that you're targeting, in this case 12, is inside the interval, what does that mean? Retain, yes, not significant, and that is within expected fluctuation. If the population mean is outside the interval, then what is that?
Significant.
Significant, and the other R word? Reject, and not expected. So if you reject the null hypothesis, that's significant. If you retain the null hypothesis, that's non-significant. Homework question. Yeah.
From the standard error, ask you or T what you
Which one?
standard error,
So like when we have
This?
when I was like, I didn't
go
realize it
to the
one
box, inside the
Like,
box,
that's significant,
standard
but if you
error equals ask
point
T.
2 times a day, that's significant. That's like
A
square
square
root.
root.
Regular.
Oh, this?
Oh, right.
Oh, yeah, sorry, this means square root. I'm just giving you the formula.
I got used to the.
The radical sign?
I could have said lost, but I said game.
Yeah, sorry, that's radical. All right, so in this case, what is this p-value telling me?
Oh,
Right here. Hmm? Probability of what? The sample mean if what is true? The null hypothesis. So, and do I have a thing here? Yeah, I have a thing.
You have some over here too.
Oh, good. I did not to draw, but since not everybody's here, well, we're going to make it worth your while to be here, right? Yeah, that's my best guess is a t-distribution. So if this right here is HO equals 12, am I on the right side or the left side with my sample mean? Right side, yeah, I'm out here somewhere. This is my mean of 13.8. You make this table come down. I think it's. That help?
Yes.
See, these are the things you should tell me. If the computers are blocking your way, that's an easy fix.
I didn't know what you did.
I didn't know you had.
I know, right? It's fancy.
I was impressed with your knowledge of that
This is
table.
the root.
Well, I only discovered it because I was used to it up high, and then one day I came down back and it was here, and I was like, didn't it used to be up? And then I realized there was a lever. So yeah, we're out here. So the purpose of the standard error is to give us some way of mapping the statistic that we're talking about onto a t-distribution where we know the probability of something happening. So 13.8 is way out here. How far out is it? It is like 5 standard deviations. That's what that means. Do you remember the percent of time that goes with standard deviations? It's like 67% are within plus or minus 1 standard deviation, and then 95% is plus or minus 2, 99% is plus or minus 3. So 5 is way the hell out here. 5 point something. Technical term, way the hell out there. Very, very unlikely that we would get a sample mean of 13.8 if the population mean were 12. Very unlikely. Reject HO, significantly different than 12. Significantly greater than
And
12.
because that's like point, and then there's 3 zeros, like 1 to 1 10,000th, I don't know that part, but, so does that make it like extra significant? Or you don't do that?
You don't do that.
Okay, good to know, because I mean, I
You
wouldn't
can
be
think
using
of it that way,
extra,
but just don't
extra,
say it, okay?
Okay.
Yeah, it would be like if you move the decimal over 2 places, it's less than 1% of the time you would see this happen. Or actually, no, in this case, this is less than, what is this, 10,000th? Oh, it's less than 0.01% of the time. Less than, okay, I'm screwing this up. Someone help me. Math people.
0.1%.
0.00. 0.1 or 0.01? I don't know. Not likely. How's that? Not very likely. Yeah, extra significant. Yeah, but remember what goes into extra significant, right? The standard error? Sample size and variance. So the bigger your sample, the easier it is to get out into the tails because the smaller your standard error is. Let's see. Same question. Let's see, this is Stata. We did that one already. You're going to get to do this one too, testing a proportion against a hypothesized value. Exact same idea, just the difference is that we swap out z for t because we don't have to worry about variance. So one thing that's tricky is that the proportion that you're testing depends on your software. SAS tests the proportion of the 0 category. Stata tests the proportion of the 1. So on your homework, I'm warning you, there's one question where I ask you about the 0 and another question where I ask you about the 1, because I want you to have to wrestle with this. Because it matters to the extent that you're testing anything other than 50-50. So in this case, I'm testing whether or not the distribution of gender is different than 50-50, where the test would be the same either way, but the confidence interval depends on what it's the confidence around. All right. So this z then is positive because this 0.6 is greater than 0.5. How do you get the other one? You're going to have to do this, recode. There may be a way to ask SAS to do the other one, but this is the most straightforward way, is to change what 0 means. Then, if you flip what's 0 and what's 1, you can get the other one instead. All right. So in this case, let's do this one. We're testing the proportion that is 39 against 50. So here's my confidence limits. So they go from 0.29 to 0.49. So what does that mean? What do you think about that relative to the 50-50 expectation? Well, first question, is 0.5 within this window? Nope. So what did we conclude about the proportion of males in this sample?
That they're disproportionate.
They're lower, yeah, because males are I guess I'm flipping it back around. We're testing the proportion of females because this is this, so yeah, there's too few females in this case. And because 0.5 is not in the interval. How likely is it? Well, we get a z of negative 2.2. So now we're over here. If the null hypothesis this time, the center, is 0.5, our negative z puts us out here. Z of negative, negative 2.2. Yeah, so how likely is it that we would get a proportion of females of 0.39 if it's supposed to be 0.5? Not very likely. Less than 3% of the time. How are we doing?
So
Nope. Okay, so is this retain or reject?
Reject.
Significant or not?
Yes.
Okay, good. Keep those together. So these are both examples of when the null hypothesis is not 0, but it's something. The idea is that it's a benchmark that you're comparing something to. All right. Then we get into our friend correlation and covariance, right? The quantitative variables. I'm not going to make you worry about covariance, but I will make you worry about correlation. Pearson kind. So here's an example correlation table. They don't bother to give you the test statistic, but it's a t. So that's where this p-value comes from that goes with these correlations. So a correlation of 0.45 between education and income means what?
it's like noisy.
A little noisy, but there's a signal there. Which way does it go? Positive. So what does that mean in terms of the variables here? More education is associated with more money. Like really a lot more money, or just like eh? What would really a lot more money be?
1.
Yes. What would really a lot less money be?
-1.
There you go. What would be completely?
0.
Oh,
0.
okay.
There we go. Yeah. So rather than just making noises, which are difficult to put in a results section, p-value. Right? This p-value is a function of two things, sample size and effect size. Those are the two things that go into t. T gives you p. So in this case, it is very unlikely that we would find a correlation of 0.45 if the true correlation in the population were 0. So it's the same idea. We're out clear on the right side somewhere. I don't have the t to mark it, but I can tell you based on the p-value that it's way out here. Question? No? Just thinking? Thinking face? Okay. Another way of thinking about that is to look at the confidence interval around that correlation, which is right this line right here. I'm not going to ask you for this because Stata doesn't do this without adding on an extra thing, and I don't believe in hand calculations. But the confidence interval around this correlation is 0.27 all the way up to 0.6. So the confidence interval middle is the correlation estimate, known as the point estimate. The interval describes 2 standard errors roughly around either side. So because this interval does not include 0, reject HO, significant, unlikely we get a correlation this big if the true correlation were 0. Okay. And then pictures, results. We did Spearman, same exact thing, although it's meant for ordinal variables or variables that have possible outliers where you want to try and control for that. We're not going to do that because Spearman doesn't show up in modeling. So I just wanted to make sure you know about it, but that we're going to ignore it the rest of the semester. And then we did crosstabs. I don't think we've done this yet. Did we do this? Okay, let's make sure we do this. And I caught an error in my own code where I had forgotten to write down these options in your handout, so make sure you write these, because they're in the example code, but they weren't in the handout. So I just caught that when I was making your homework. So I think you have rel risk, but you don't have risk diff or expected.
Where don't we have that?
On this line right here on page 12 of example 3. Unless you just re-downloaded it just now, in which case it's there. Okay, yeah, if you downloaded it when I posted it and have been adding notes to it, I didn't want you to have to re-download it, so you can just add that. But yeah, anytime I find an error, I post it immediately, a new version.
So all we're missing is risk diff and expected.
Expected. Yeah, you're going to need this one for sure. So chi-square. What's chi-square for? Categorical. Yeah, association. It's not linear, it's not anything that is numerically specific in the same way that Pearson's correlation is, it's just association. And it's based on a deviation from expected frequencies across pairs of variables. So in this case, for instance, I have, using the GSS data, I'm looking at whether or not someone thinks that females are not suited for politics. So saying yes means bad Hillary Clinton, Elizabeth Warren, etc. No means okay. So this is sort of like misogyny or something. It's a fun variable. And whether or not they're married. I thought there might be a relationship there. Let's find out. So there are 49 people who are okay with women in politics, 18 people who said nope, and there are 28 people who are unmarried and 39 people who are married. So expected number of people from each cell, if there were no association, is given in your handouts. Let me go back to get that so you can see where it's coming from. The expected cell count is the number in the row column times the number in the row times the number in the column divided by the total. So in this case, the number of people who said no and are unmarried, if these variables have nothing to do with each other, should be 49 times 28 divided by 67. SAS or Stata will be happy to spit out that number for you as this one. So this is the expected count. So there's actually 18 people who fall into this category. The model thinks there should be 20. Likewise, there's actually 31 people who fall into this category. The model thinks there should be 28. So it looks like there are slightly more people who are unmarried and think that women in politics is okay. Now, is
that okay?
Is okay. So this is a variable where they're saying that one means not. So no means okay, one means not okay. So the question is this 18 versus 20 something to make a big deal about? Well, what we end up doing is the chi-square. Come back. There we go. It is right here, the formula for it. Observed minus expected squared to make sure that the differences don't cancel each other out, divided by expected, summed across all the cells. So that number is right here. There are a million very similar versions of this that they also give you. You have my permission to ignore them. Someone else can worry about those distinctions. So chi-square is 1.9. That is referring to a chi-square distribution. Degrees of freedom, number of rows minus number of columns, number of rows minus 1 times number of columns minus 1. In this case is 1. So critical value for chi-square is 3.84 on 1 degree of freedom. That gives us exact p-value. So chi-square needs a new picture. Remember what chi-square looks like?
1/2.
Yeah, half of it. Chi-square is only positive. So chi-square kind of looks like this. Yeah, you need the sound effect. Otherwise, it's not as good. So 3.84 is the point where we say the area out here is less than 5% of the time. But we are where? Are we out in the tail? We're over like here, 1.9. So in this case, what do we conclude? Not significant, which is paired with do not reject or retain. Never accept though. See, it made me so flustered I dropped my marker. Think about accepting. So yes, this wiggle, this 18 versus 20, 31 versus 28, 8 versus 10, 10 versus 7, that wiggle is not enough to say that it's unexpected. It's within expected territory. So chi-square is our test statistic. Test statistic. That's really hard. It's not an effect size. Like if I told you you have a chi-square of 30, you'd be like, is that good? The only way you'd know what that means is relative to degrees of freedom, but even then you don't have a sense like in the same way that you have a sense of what like R means. So we need an effect size to go with this. You've got lots of choices, one of which is R. You can take your chi-square test statistic and convert it into an R as such. If you don't want to do the math yourself, can you guess how you would get an R out of this chi-square table? Don't think too hard. How did we get a correlation before? No hand calculations. None.
Oh.
No hand calculations. How do we get a correlation? Pearson's correlation, in fact.
You just divide by the square root. Nope.
Well, that's how you would get it. But if you wanted SAS to make it for you.
I prefer that.
Do you know how to do this already? Yes, Michael?
Would you just do
Yeah. Say it again, louder.
You do Proc Core.
Yeah, you know how to make a Pearson correlation. We did that like 2 pages ago, right? Proc Core. Yeah.
Where?
Hmm?
Where do we put that?
Where would you put that? You would make, you would, you do a new one. I believe there is also a Pearson correlation option on Proc Freak. If I remember correctly, it is P-Core, but I'm not 100% certain about that. Let me find out. So this is me preparing your guys' examples for things that I haven't done before. SAS, Freak, Pearson, correlation. Oh, look, someone's asked for that already. Then we get to Proc Freak, chi-square tests and statistics. That seems promising. So welcome to the SAS documentation. Syntax. My guess is that it's going to be on the table statement because that's where the other ones are. And we go down here and look at the list. Look at all this stuff I can ask for. I don't see it. That's polychoric correlation. That is something else. Let me look on Proc Freak. Let me see if I can put it there. No, maybe it's not on this one. I want to say I saw it at one point. So, but given that I didn't give it to you, running Proc Core would be just fine. So that would give us some version of effect size. However, what if I told you you didn't have to do that? You'd be happy? Remember what a synonym for Pearson's correlation is for binary variables? He has a special name. Phi. There it is. Phi.
Phi.
Phi. Yeah, P-H-I. Yep.
Oh, so that's it?
Yeah.
That's our, what are we looking, we wanted to correlate, that's our R?
Yep, that's an effect size. So now you know what to do with this, right? If I told you this is R, it's negative, right? So you know what negative means. It's this one. Now you gotta think about that, what that means in the context that we're not talking about numbers. It means that being married is associated with being more likely to be okay with women, the lower of the categories. A higher value on this variable is more likely to be associated with a lower value on this variable. And you can confirm your understanding of that by looking at this. Yes, there are fewer people here than expected. So the null hypothesis of zero correlation is given by these expected frequencies. The extent to which your data deviate from expected in the direction gives you a sense of the direction of the association. There are more people in this cell than there should be. A little bit. So now we've got everything that we would need to be able to talk about this. We've got a test statistic, the p-value that goes with the test statistic, and then we have an effect size. So let's say that you wrote this up. You wrote this up, you submitted it for publication, and reviewer 3 is not having it. I think that your conclusion that there's no association between misogyny and marital status is suspect because you don't have enough power. I'm not making this up. This is a very common thing. There's things that are like in the reviewer nitpicky handbook. Missing data, power.
See, I would read your comment and I'd be like, power. I would think that totally differently. I would not.
What are they talking about?
You're not being critical.
They're talking quantitative power.
Statistical power. What is statistical power? We talked about this last time.
Beta.
Beta, yes.
The opposite of alpha.
The probability that you will find what you're looking for if it's there, yes. What is power a function of? Two things. One of them is effect size, such as given by this Pearson correlation. What else? Nope. P-value is also a function of those things. P-value and effect size lead to power, but what leads to P-value? Yes, I will take that, but not what I wanted. The number of people, yeah. So you remember the story about the delay of gratification and how one condition had a significant positive correlation of 0.4 and another condition had a non-significant correlation the same size because it had half as many people? So what your reviewer is saying is that you lack power to find an effect that's this big. Well, no shit. This is a tiny little effect. It will take like a lot of people to find it. So they're not wrong. How do you estimate power? Well, just run G-power. That's one way. We can do empirical power analyses, but you can get a sense of it from looking at these power tables, right? So that correlation, let's round up to 0.2. And I've got a sample of people who completed this question of 67. So I am under this cell right here. So yeah, I have less than a 25% chance of finding a correlation about 0.2 if it's there, given my sample size. So I can't dispute that. They're right, I have no power. The question is, do we care about a correlation that small? That's the argument that you have to make. Even if it were significant, would it be worth writing a paper about to find a correlation of 0.2 or 0.17? That's where you got to go. And that they can't argue with because that's a theoretical question, not a statistical one. Now, what if reviewer 3 is also picking on us, go back here, about our correlation between income and education? It's always reviewer 3. Always. Go back here. This one. What if they say, I don't think you had sufficient power to find that correlation? Now what? Valid point or what? Yep. The question, the statement reviewer 3 is making now, I don't think you've had sufficient power to find this correlation at 0.45.
What was our sample size for that?
This one is 96.
Was that the example you asked for?
That one is about a small effect size and trying to come up with relative risk or odds ratios to describe that effect size. So related, but not where I'm going with this.
They're wrong, aren't they?
Yeah, they are.
Because according to that chart,
Small p-value?
Uh-huh.
Yeah.
Significant. We can't, power is not a problem if something is significant. By definition, you had enough. You found it. It may not have been likely, but you found it.
0.99 power is 105.
In the power table, so what is it for at 96? What is the power at for 0.45?
I just went down to 0.4,
Mm-hmm.
and it's for, oh, maybe I did it wrong.
No, you're about
Did you
here.
look at the R,
Oh, that's
the
D.
R one?
Yeah, sorry, I'm on the wrong page. No wonder. That's okay.
Right?
Here we are. We're somewhere just under this. In R. Yeah, I was looking at D. Sorry, D's a whole nother one. You'll look, we're getting to that one soon. Yeah. No, we had enough power because we found it. Remember the ways that you can screw this up? Decision errors. We started talking about this last time. if we say something is significant, which row of this table are we in? Bottom one, reject land, reject significant, reject is significant. Therefore, we have two alternatives. There really is an effect and we found it, hooray. Or we're saying there's an effect and there's really not. So these are the only two possibilities conditional on the fact that we have already rejected HO. Power is not a problem by definition. Now, how do we answer this? What if the reviewer says, I think you made a type 1 error? So let me back up. What the reviewer is saying when they say, I think you have a problem with power, if they're saying you have low power, that you have a high chance of a type 2 error. You have a high chance of missing something that is actually there. You have a low chance of finding something that is actually there.
Maybe you need to get more people.
You would need to get more people to get more power. It is that simple. At the same level of effect, you need more people for higher power. So if you want high power, you get a strong effect and you get lots of people. But type 1 error, can we answer this? How likely is it that we've made a type 1 error in saying that our correlation of 0.45 was significant? Do we have that?
Very small.
What? Yeah, no, you're talking.
It's very small. So
What's very small?
The p-value.
The p-value is our type 1 error rate. That's what it means. It's the probability that we would find a correlation of 0.45 if the true correlation were 0. And our p-value was less than 0.0001, meaning really unlikely, but still technically possible, just unlikely. So putting this together, when you say there's no relationship, when you say that whatever you've found is within expected territory, you have to worry about the chance that you've missed something. The chance that you've missed something is your type 2 error. The chance that you haven't missed something is power. Power is the likelihood of finding something that's there if it's there. If you decide that you have an association, you found something, you're going to write about it, then you have to worry about the chances that you would have found it by chance. That's type 1 error. How likely is it? And so when we set an alpha level of 0.05 for our tests, we are accepting that 1 time out of 20, 5% of the time, we find something that is not really true as a fluke. Say it again?
Yeah.
Okay. When we set an alpha level of 0.05, or saying that the same way differently, when we set a confidence interval of 95%, confidence interval of 95% for how much is expected, 5% on the tails of unexpected. When we set that, what we are saying is that 1 time out of 20, 5% of the time, we're going to find something as a fluke. So if I run 20 correlations and I set my a priori alpha to say that if it's p less than 0.05, I win, I'm going to win once. Odds are good I'm going to win once out of 20. That's what it means. Now, what if that's unacceptable? What if you really hate the idea of saying you found something and being wrong? How do I fix that? How do I make it less likely that I would be wrong? Lower my alpha. What if I picked alpha of 0.01 or 99% confidence interval? Then how many times out of 100 am I going to be wrong as a fluke? Once. I can live with that. So there's a trade-off. And the trade-off is shown by this picture. So let's start with the black one here, this one, okay? This is the distribution if the null is true. So if the correlation is 0, or if the population mean is really 12, right? Whatever your anchor point is. The gray part of this distribution is where 5% of the time is. It's on both sides. So the 5% anchoring down here. So if the null hypothesis is true, if there is no correlation, for example, you will find a correlation that big this percent of the time. If you want to have fewer type 1 errors, if you want to be more certain that you're not just finding things as a fluke, you reduce your alpha level, increase your confidence interval, say out to here. Now the range of what is expected is much bigger. It's harder to get out into the tails. It takes a bigger effect to get you out there, or more people, or both. And so then that is like this bright red out here. Much less of the time you would be saying that something is unexpected.
So why would you do that? Why wouldn't you always lower your alpha so you have less error?
Yeah. Great question. Here's why. You don't want to miss anything. So let's say that this is the alternative distribution. Like this is my correlation of 0.45 that I found. These distributions overlap. So the idea of this red section here, like if I believe this is reality, that there is this correlation out here, and I'm testing it against 0, this red shaded area gives me the percent of time that I am going to say that it is not significant. So it's either this much or this much. That's a type 2 error. So the lower your alpha, the further over you're getting into this distribution, the more likely you're going to have to say, nope, it's not really there. It's part of this distribution, not that one. And so moving alpha over makes it less likely that you find a fluke. It also makes you more likely you're going to miss something. If I had an alpha of 0.1, 10%, if I move it over this way, right? Now fluke is more likely, miss is less likely. The other side of this here is power. We're off of the null. This is your power to detect your effect. So there's trade-offs. I can tell you what is convention. By convention, in the social sciences, alpha is almost always 0.05, and power is desired to be 0.8, which means the type 2 error rate is 0.2. I'll say that again. If power is 0.8, 80% of the time we will find the effect that is really there. Then 20% of the time we will miss the effect that is really there. Power of 0.8 means 80% of the time we will find the effect that is really there. 20% of the time we will miss the effect that is really there. That's beta. That's type 2 error.
And even if you have that, the 0.8, would you get questions back from reviewers? Questioning power?
It depends on what you're claiming. So if you have a significant result, power is by definition not applicable. If you have a non-significant result, you have to be able to say that it's because it's a small effect, not because you have no power to detect a decent effect. So if we go to the table, just give you a couple examples here. Here it is. Here's R. Let's say that I am going to do a pilot study and I have 10 people. Could happen, right? Especially if people are hard to find. Like you're studying a really rare phenomenon, or it's really expensive to test them, like if you're doing neurological testing or those kinds of things, like in an fMRI or EKG, that kind of stuff. Well, here's 10 people. Here's 10 people. Here's 10 people. So that means that if you want to have 80% power with your chosen sample size, you need to have an R of at least 0.8. Good luck with that. But where that information can be helpful is, let's say that you get an R of 0.3. It's not going to be significant. You have no chance in hell of finding R of 0.3 is significant with 10 people. But if you trust your 10 people enough to say that, no, this is what I could expect if I had 100 people, then this gives you a sense of how many more people you need to have a decent chance of saying it's significant of rejecting the HO. You need 85 people to hit a power of 0.8. So when you have a non-significant effect, you have to ask yourself, do you not have enough people to find something big, or do you not have an effect worth finding? Two different things.
So,
Question?
yes, and, okay, so power is the one going down the column, and then this 0.10 through 0.9.
Is the
This
metric
is your-
of the effect size.
This is your effect size.
Yes,
So
R.
the one closer to 0.1 is better, or is it not like that? I think I'm getting confusing of what,
Okay,
confused
so
what
yeah.
R equals.
So R is going across the top.
Uh-huh.
Going down the side is your power, your probability of finding that R if it's really there. The values in the cell is the number of people it takes to hit that level of power for that R. And so there's two ways that you can use this table for study planning purposes. And this is a very simplistic version of it. If you have a more complicated model, then this may not be adequate, but this helps. This for bivariate association is totally fine. So you can either say, I think I'm going to have an R of 0.3 based on my pilot study or based on what someone else has found, right? I believe in 0.3. What is the trade-off of getting more and more people? Right? So there's a huge increase in going from 20 to 40. Power doubles. Going from 40 to 50 to 60, this is the point where it starts to level out, right? You don't get, like, more and more people doesn't help as much as it did initially. So you can use this expected effect size to figure out how many people and whether or not adding more people is going to help. So for instance, if you're questioning whether you need 60 people or 80 people, right? That's somewhere between here and here. That's like 0.65-ish versus 0.77.5, right? So you can use this to decide at what point you're happy with that. The other way of doing it, which is much more common, is that you have a fixed sample size. I have 30 kids in Miss Smith's class. That's what I got. And tell me what I can do with that. Okay, let's go find 30. Here's power of 0.8. There you are. You have adequate power with 28 people to find an R of 0.5 or greater. If you're willing to slide down on your power, let's say that you want to go to power of 70%, 30% chance of missing an effect. Then you can go down to about R of 0.45.
And that's what makes it significant.
That is your probability of finding it to be significant at that sample size, if that is your effect size. But it's still a probability. It's not a guarantee.
And then, so I think where I'm also getting confused is I'm like losing the scope of R.
Mm-hmm.
So do we want, I forget like how we want our R to be.
Oh, who can help her? What do we want our R to be? What's the best R you can have? 1 or?
Oh, gotcha.
Yeah. What's the worst R you can have?
0.
Yeah. So what if I have an R of negative 0.3 that I'm after instead of an R of 0.3? Does that change anything?
No.
Nope.
I guess I don't understand why you'd be after an R. Wouldn't that be something you'd find?
It is, it's something that you want to find, but in order to be able to have a good probability of finding it to be significant, right? You can find it regardless. The question is whether or not it is different than 0. This table is all about getting you to different than 0.
And so then, but 0.9 would be closest to 1 or -1.
Mhm.
But then why does it seem like that one's easy? Maybe it's not easier to get, and I'm not
It
understanding.
is way easier to get. Yeah, you only need 6 people. If you have a near perfect correlation you're after, that is a huge signal.
Perfect is perfect, is what they're saying.
It only takes 6 people to demonstrate it.
I see now how this
Mhm.
works. Yes.
How much more is
Enough? 80% is the classic definition. But I think that's in social science. I think in reality, it depends on the context of what you're doing and whether or not it is more problematic to have a fluke or a miss. That's, if you think about drug trials and things like that, right? If you're looking at like screening for cervical cancer or something, and you have a test that has more false positives, well, a false positive then gets you into your doctor's office for more testing, and maybe it comes back negative or maybe it's okay. So maybe you're okay with more flukes, but you certainly don't want a false negative. That's a big damn deal in the context of screening for cancer. And so in that case, you would change it so that you have a high type 1 error rate, but a lower type 2 error rate. You don't want to miss anything. In contrast, if you have something like you're evaluating students for their likelihood to grow up and shoot all their classmates, sad but true. These are real life things, right? That we're social scientists are studying, and you want to be really hesitant to put a label on a kid that travels with them that they're going to be a problem, right? A fluke is a big damn deal in that case, but I guess so is a miss. So there's no right answer. It's what the context of what you're doing. But it's all probabilistic. So it's not enough, I'm saying, to say reject HO or retain HO. That's not enough. Because that just means you have enough of a sample to find something. What did you find? Effect size. So every thing that you've learned so far, let me make this big. We can categorize here. So we have a statistic. We have some way of getting a standard error. We have a test statistic. And that test statistic gives us a p-value. So, no, fine, don't give me an arrow. Grr. So if we have a sample mean, for instance, right? We can compute a standard error of the mean. If we want to compare our sample mean to a population mean, what's our test statistic? Because it's sample mean minus population mean over standard error. I'll tell you that's what it is. What's the letter? T. If
you don't have an infinite sample?
If not infinity and or. What else? What about variance? Variance is known or unknown? T. T is unknown. T is unknown because then we have denominator degrees of freedom, and we got to have that. So then we have our T distribution.
I was impressed by your Excel skills.
Thank you. Thank you very much. I'm here all week. SEM Z if infinity and or known variance. So this is the case where when you do a test of a proportion, because you don't have to estimate variance for a proportion, it's given by the mean. It gives you a Z instead. Known variant, unknown, var, Z dist on that one. What's the difference between T and Z if I drew a picture?
Too flatter.
T's flatter, but they're both two-sided symmetric, right? Yep, so you know that one. Let me add to this. Effect size, there's another column. So, we also learned covariance, right? What's covariance? Gabby, what's covariance?
I don't know.
Okay, phone a friend. You want to toss it to someone else?
I don't know if it's, well, is it the same as the one we talked about at the beginning of class? Where other people care about it? Or is it a different context?
You will need to care about it if you take more statistics. But what's the difference in correlation and covariance?
Cohabitation, co-sleeping, I remember the examples. But
Togetherness, yes. It's the scaling, right? Covariance is association in units of y and units of x. You can correct for differences in scale and it becomes a correlation. You can compute a standard error for a correlation, but it requires a nonlinear transformation to do that because correlations are bounded. What test statistic do we test a covariance or correlation against? That's the effect size. Yep. R is the effect size. What is the test statistic that comes up to test an R against null hypothesis? Give you hints up here already. Pick one. T or Z?
T.
T, yeah. Just T always. T. Yeah. And the T distribution then gives you your p-value. And we also learned Spearman's falls under this category. Just using ranked order data, nothing changes. How about chi-square? We have a measure of association that is computed directly. And then this is the chi-square distribution that goes with that. What kind of effect sizes could we use with the chi-square for categorical data?
R.
Yep, R is fine. Think ratios. The one I hate.
Or is that something?
What is it? Phi? Nope, phi is the same thing as Pearson's R for binary pairs data. Odds, yeah, odds ratios. Also risk ratios go in there. Yep. So the categorical data one looks a little bit different than the others because there's no statistic that is computed that is you have to then transform into a distribution. It's chi-square directly. All right. Questions? So where we're headed next? Previewing where we're headed next. General linear models. We're getting into models. It's going to be fun. But what we just did is review this slide. Bivariate association. What do we use models for? The idea,
Can you go back to
Yeah.
one split second?
for which one?
The Excel spreadsheet.
Yep. I need to wrap the text on that. There we go. Yeah, that's the one that doesn't look like the others.
So is the statistic next to the effect size R, so that we don't have a statistic?
I mean, you calculate the test statistic directly. There's not another thing that you then have to translate into it. So like for Pearson's correlation, it starts with covariance. You can translate that into an R. You take that R and use the formula that goes with the sample size to get a T, and then the T gives you the P. Right? Like it's a series of letters that you have to get through. Chi-square for categorical data is just different in that regard. So what are models for then? And why am I starting with models already? Guess what, folks? By the time we finish with this next unit, this next example and lecture, you will have learned everything that they learned last year in 6242.
Whoa.
By the end of week 6. Then we get to do everything that you would have learned in correlation and regression in this course, because that's how I roll. But what are models for? Associations among more than 2 variables at a time. So classic example, what if I told you that murder rates are correlated with ice cream sales? Have you heard this before? Why are murder rates correlated with ice cream sales?
Summer?
Temperature. So one might ask, after controlling for the fact that people buy more ice cream in the summer, is buying ice cream related to murder? Probably not, right?
Causation.
Unless your ice cream headache is that bad. Or is screen time bad for your 4-year-old? I'd like to think no, because otherwise I'm never going to cook dinner, take a shower, fold laundry, or otherwise have a moment of peace, right? Screen time is my favorite time. So I'm like, it's not bad, it's not bad. It's not that I'm just sticking him in front of the TV for the rest of his life. Like, if he wants to watch Peppa Pig, like, Jesus, like, is that such a problem? No. But then you think about what goes into kids who have an excessive amount of screen time. What are their parents not doing with them instead, right? So is screen time bad after controlling for amount of time you spend reading to your child or talking to your child, or socioeconomic status, or what if your kid is hospitalized because they're undergoing cancer treatment and Peppa Pig is the only thing they can do? Like, there's 1,000,001 reasons for associations, and there's oftentimes research questions are phrased as, after considering these other things, is this relationship still present? You cannot answer those sorts of questions with just bivariate association. So we need models. Likewise, you can't examine non-linear relationships among quantitative variables without models. It is very difficult to examine relationships between nominal variables and quantitative variables without models. So where we are headed next is being able to answer those sorts of questions, to be able to predict a quantitative outcome from any kind of predictor, any combinations of predictors, as well as, eventually, interaction terms. It is going to be exciting.
I'm quantum now, man.
It
I
is
am
exciting
converted.
because this is the point where you are literally able to do something with your own data that you care about. Because you're never going to care about like a one sample mean. Like that's an excuse to get you into the idea of hypothesis testing, right? It's not usually something that's of great interest. But these are the kinds of things that readily translate into a master's thesis, a dissertation, publications, and that kind of stuff. So I'm excited, and I want you to be excited. Are you excited?
Nope, scared shitless.
If you're still scared by week 6, Yep.
Every day.
Of me?
No, not of you, of course not. Of this.
Words.
This is scary. Words.
I love words, Karen.
Yeah,
Like
so
words.
remember
I
what
like
I asked of you on the very first day, right? I told you don't have to read your textbooks. I gave them to you because I feel compelled to. But what did I say? Drill vocabulary, right? Like honestly, make flashcards if that's what it takes. Drill letters, vocabulary, concepts. Try to figure out like which proc goes with these ideas, right? You don't have to memorize the SAS code, but just having it in your head, okay, proc core, what does that give me? Proc freak, what does that give me? We're gonna get to proc GLM next. So those are the kinds of things that can help, because honestly, managing working memory is the hardest part of this. Working memory load is why statistics is hard. Because I'm not making you do the math, right? I'm not making you memorize the formulas. And actually, I'd prefer it if you don't do things by hand. Because by hand is how you screw things up. Because the computer is just better at it than you will ever be. So, keep it in the spare time that you have, work with the software, work with the material, try and drill yourself so that this stuff just rattles off the top of your head, right? That will help you. And don't be afraid. Because that just gets in the way, right? Easier said than done, I know. But if you want to have any extra time with me to go over things and alleviate anxiety, I am happy to do that too. So, all right. Then we have a nice, exciting place to start next time. Look for an email from me either later today or tomorrow letting me know when the quiz is up as well as homework too. All right. All right. Have a great weekend, folks. Thanks.